When finding the zeros of this polynomial, we'll point out a theorem that's true of all polynomials. Every polynomial can be uniquely factored over the real numbers, which means that the coefficients of the factors are real, into the product of linear and irreducible quadratic factors. And when we factor this polynomial over the real numbers, we'll come back to this theorem to make sure we understand what it's telling us. Find the complex zeros of this polynomial function. In other words, find all the zeros. And since we have a fourth degree polynomial, we know that we're expecting 4 of them. Our process is that we first start with the P over Q list, which we then cross-reference with the graph. So let's start there. P is the constant, Q is the leading coefficient. All the factors of P are plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, plus or minus 16, and plus or minus 32. All the factors of Q are plus or minus 1, plus or minus 2, plus or minus 4. And we need to consider all possible combinations of every factor of P over every factor of Q. We start with the first factor of Q and write all factors of P over it. All the factors of P over 1 is just a duplication of the P list. So this is all the factors of P over 1. And now we look to all the factors of P over 2. 1 over 2 is 1/2. 2 over 2 is 1, but we already have that. 4 over 2 is 2. We already have that in our list. 8 over 2 is 4. We already have that in our list. 16 over 2 is 8, which we already have. And 32 over 2 is 16. Again, we already have that one. So now we have every factor of P over 2, and we move to the third factor of Q and write all the factors of P over 4 now. 1 over 4 is 1/4, so we need to pick that one up. 2 over 4 is 1/2. We have it. 4 over 4 is 1, and we have that one. 8 over 4 is 2, we have that one. 16 over 4 is 4, we have that one. And 32 over 4 is 8, which we already have. So when writing all the factors of P over 4, we only picked up the one additional element, 1/4. So now we're going to cross-reference this with our graph. We come over to our calculator, into the y equals field, and we input our function. 4x to the 4th plus 7x cubed plus 62x squared plus 112x minus 32. And when we come over to our graph, we can barely see any of our graph at all. We could play around with this window here a little bit. It does seem like something else is happening right here. So if we shrink our window down to having an x minimum and an x maximum of 5, that would zoom in on this region a little bit and hopefully reveal what's going on. Let's try that. So window from -5 to 5 on the x's, and that being the only change, let's see if that reveals anything for us. And it kind of does. I'm feeling more confident about x is equal to -2, and again, we can double check that to say second calculate the value. Plugging in -2, we can see definitively that it actually is an x-intercept, and therefore -2 will be a 0. So that's definitely going to be where we start. This could be positive 1/4. Let's try that. Evaluating 0.25 for x, and we do get confirmation that that is another x-intercept. So these are definitely going to be the two zeros that we turn into factors and use to begin factoring this polynomial. So let's begin with the 0, x is equal to -2, which tells us that x plus 2 must be a factor of the original polynomial. Since it's a factor, we can divide that factor out. We know that it's going to divide in evenly. And when we divide it out, what we get as a quotient would be another factor of f. So we begin with our synthetic division. This is our divisor, and the original polynomial is the dividend. The 0 of the divisor goes into this box, and let's just notice that that's going to be the same as the 0 that we are verifying. And the coefficients of the dividend are written down to the right of the box. We need to be careful and double check that we have all of the powers of x and we're not missing any terms. Any missing terms would need to have a 0 placeholder in the synthetic division. We leave a lane of space and draw a horizontal line here, and then we begin the division process. So we bring down the 4, multiply on the diagonal. That product comes up under the next coefficient. Combine down to get -1. Multiply on the diagonal. -2 times -1 is +2. Combine down to get 64. Multiply on the diagonal. The product is negative 128. Combine down to get negative 16. Multiply on the diagonal to get positive 32. And combine down to get the remainder of 0, which is what we were expecting since we already saw on the graph that this is a 0. We're using synthetic division in order to help us factor that fourth degree polynomial. So every time we get a confirmed 0, we want to pause and begin that factorization process. So we just saw that x plus 2 divided evenly into the polynomial, and the other factor that remains when we divide that out is going to be the quotient that we obtained through the division. And these are the coefficients of the quotient. Since we started with the fourth degree dividend and we divided out a linear divisor, the quotient is going to be third degree, which means that 4 is the coefficient on an x cubed term. So we have 4x cubed. Negative 1 is the coefficient on the x squared term, so minus x squared, plus 64x, minus 16, and now we factored out our first factor. From here we have two options. We could use the fact that 1/4 is another x-intercept and therefore a 0. We know that that's true, so we could use that 1/4 0 to help us continue factoring using the synthetic division method. Or you might notice that this third degree polynomial does factor by grouping. So we could proceed down either one of those paths to continue factoring this polynomial. But this time I'm going to continue with the synthetic division and use the fact that we know 1/4 is a 0 from the graph, which gives us a factor. We know that x minus 1/4 must be a factor, which means that x minus 1/4 must divide evenly into the function. And if x minus 1/4 is a factor of the original polynomial, it must also be a factor of this polynomial because this is the only one that's going to factor farther. This linear factor is prime. It's not factoring anymore. So instead of going back to the beginning, we're going to divide x minus 1/4 into this quotient, which means that we just draw another backwards box here and keep going with the synthetic division tower that we've already begun to build. The 0 of the divisor is what goes into the box. We draw a line, leaving a lane of space, and we begin the synthetic division process, which begins with bringing down the 4, multiply on the diagonal. 1/4 times 4 is 1, and that product comes under the next coefficient. Combine down to get 0, multiply on the diagonal. 1/4 times 0 is 0. Combine down, we get 64. 1/4 times 64 is 16. And finally, we combine down one more time to get a remainder of 0 again. Every time we get a confirmed 0, this is where we want to pause with the synthetic division and go back to the factorization. So we copy paste the x plus 2 factor, and we just divided out the factor of x minus 1/4. So we have x minus 1/4, which is then going to be multiplied by the quotient that we obtained from the synthetic division. This quotient must be quadratic since we started with a third degree and we divided out a first degree. So 4 is the coefficient on x squared. 0 is the coefficient on x, so we have 0x, and we don't need to write that. And 64 is the constant, so we have 4x squared plus 64. Now that we have come down to a quadratic quotient, this is where we abandon the synthetic division. In this quadratic factor, we do see that we have a common 4 to both terms. So we can factor out that common 4. So we pull it out of this factor, but I'm actually going to pull it all the way to the front of the polynomial. So we have that common factor of 4 pulled all the way out to the front, x plus 2, x minus 1/4. And when we pulled it out of the quadratic factor, we are left with x squared plus 16. Now, x squared plus 16 does not factor using the AC method, and it's not a special case. As a matter of fact, this is what we call an irreducible quadratic. And here's where we want to return to that theorem at the beginning of this video, which says that every polynomial can be uniquely factored over the reals, meaning that we're required to have real coefficients. Then we can factor a polynomial into the product of linear and irreducible quadratic factors. If we're going to factor this anymore, it's going to require that we are allowed to factor over the complex numbers, we're going to get imaginary zeros from this irreducible quadratic, and to factor it anymore, we're going to need complex numbers. We still haven't quite finished this problem. It says to find the complex zeros. Since we have it completely factored over the reals, this is where we're going to plug in 0 for y and solve for x by setting each of these factors equal to 0. Remember, we do not get a 0 from a constant multiple on the front. If we did try to set that factor equal to 0, we would come up with a contradiction. So we don't get a 0 from this constant multiple. We'll then set the next factor equal to 0 and get the 0 that we already knew at the beginning of this problem. Setting x minus 1/4 equal to 0 gives us the 1/4 0 that we saw on the graph. It's when we set this irreducible quadratic equal to 0 that we get the remaining 2 zeros that we didn't have at the beginning. So we have x squared is equal to negative 16, and when we take the square root of both sides, we get a plus or minus on the constant side, and x is equal to plus or minus 4i. So the zeros of this polynomial are x is equal to negative 2, x is equal to 1/4, and x is equal to plus or minus 4i. Again, notice that we have 4 zeros, which is what we were expecting on this 4th degree polynomial function. So now that we have those zeros, we're able to completely factor this polynomial over the complex numbers. We start from where we left off with our factorization, and we say now we know that this term can be factored using its zeros. So we have f of x is equal to 4 times x plus 2, x minus 1/4, and x squared plus 16 factors into x minus the 0, which is 4i, and x minus the other 0, negative 4i, which can be simplified into x plus 4i. So if we're allowed to factor over the complex numbers, we can factor the polynomial down to all linear factors. We can force factor this irreducible quadratic once we have found its zeros. In part C, it says to factor over the real numbers, but we already had that. Factoring over the reals means that it is the product of linear and irreducible quadratic factors, so we essentially just copy-paste the previous step so that all of the coefficients in the factorization are real. Factoring over the real numbers means that we get it down to linear and irreducible quadratics, and factoring over the complex numbers means that we can get it down to all linear factors.